In the previous lecture, we have discussed total internal reflection. During that discussion, we have found that although the fields exist in the second medium, that is the rarer medium, when the electromagnetic wave passes from denser medium to rarer medium, but there is no flow of energy through the surface into the second medium. So we say that when the angle of incidence is greater or equal to critical angle, total internal reflection takes place. Actually, after total internal reflection, the state of polarization of the plane polarized electromagnetic wave is changed. Actually, the reflected wave is found to be elliptically polarized into different polarization state. So now in this lecture, we are going to discuss the state of polarization after total internal reflection. We will find that although the incident wave is plane polarized, but the totally reflected wave is elliptically polarized. But how we can say that the totally reflected wave is elliptically polarized? Let us see in detail in this lecture. We will see actually in this lecture. We have already discussed in the Fresnel's equations the two very important Fresnel formula. So I have mentioned here the two important Fresnel formula which is needed to discuss this important fact. I have mentioned here. The first one is when electric field vector E is perpendicular to the plane of incidence. In fact, in that condition, in terms of refractive indices of the two media, we have found the first Fresnel formula in this form: E naught 1 prime over E naught 1 perpendicular is equal to cos theta I minus n2 over n1 cos theta r over cos theta I plus n2 by n1 cos theta r. Here you know that theta I is angle of incidence and theta r is angle of refraction. N1 is the refractive index of the first medium, that is the denser medium, and N2 is the refractive index of the second medium, that is rarer medium. And similarly, we have already found in previous lecture during the Fresnel formula that when electric field vector E is parallel to the plane of incidence, then it is found that E naught 1 prime over E naught 1 parallel is equal to n2 over n1 cos theta I minus cos theta r over n2 by n1 cos theta I plus cos theta r. Actually, we will see from these two results. First of all, the phase retardation takes place after total internal reflection, and after calculating the phase retardation, we will also see that there is no change in the intensity of the wave due to the reflection, and from that result we can found what will be the relative phase difference between the parallel and perpendicular component of reflected electromagnetic wave, and that result will give us an idea that the reflected wave will be actually elliptically polarized. So let us proceed how we can discuss these important facts. So let us see the result which I have mentioned in this equation 1, this equation A. So let us consider the first case, that when electric field vector is perpendicular to the plane of incidence. When E is perpendicular to the plane of incidence. In that condition, as I have mentioned in the result A, the ratio of the amplitude of the reflected wave, which is E naught 1 prime, and the amplitude of the incident wave, which is E01 perpendicular, this is equal to what? I have mentioned here in this result A that this is cos theta I minus n2 over n1 cos theta r over cos theta I plus n2 by n1 cos theta r. We can write this expression in RHS in this form. This can be written as alpha minus I beta over alpha plus I beta. Actually here we have substituted that alpha is equal to what? I have written alpha instead of cos theta I, and I have written I beta at the place of n2 over n1 cos theta r. I have written this. So you can see that E01 prime over E01 perpendicular. You know, if we want to find the real and imaginary part of any complex quantity and there is a complex in denominator, then there is a simple technique that we will multiply the numerator and the denominator by the complex conjugate of the denominator. So you can see in denominator the factor is alpha plus I beta and its complex conjugate will be alpha minus I beta. So we should multiply this RHS by the complex conjugate alpha minus I beta of alpha plus I beta. So after multiplying this, what will be our result? This will be alpha minus I beta into alpha minus I beta over alpha plus I beta into alpha plus I beta. And this will be what? You can see alpha minus I beta times alpha minus I beta. This will be alpha square minus beta square minus 2I alpha beta. And the product in the here actually there is alpha minus I beta, alpha minus I beta. So this product is alpha square plus beta square. And so you can write this expression as alpha square minus beta square over alpha square plus beta square minus I 2 alpha beta over alpha square plus beta square. Let us say this is equation 1. Now let us put alpha minus I beta, alpha minus I beta over alpha plus I beta equal to rho into e to the power rho into e to the power minus I delta perpendicular. And this can be written as rho into cos delta perpendicular minus I rho sine delta perpendicular. We can write it. And let us say this is equation 2. Now you can see that if we compare this equation with the equation which has been defined in the above equation here, and let us see this equation 2 and the equation defined in equation 1. So you can see that what will be this rho cos delta and rho sin delta. So comparing these two equations, comparing these two equations, we will find that rho cos delta perpendicular is equal to alpha square minus beta square over alpha square plus beta square. Real part is equal to real part. And again you can see when we will equate the imaginary part, this will be rho sine delta perpendicular. This will be equal to 2 alpha beta over alpha square plus beta square, and say this is equation 3. Now from these two results we can find the value of rho, which is an unknown quantity till now, and the value of this delta perpendicular. So you can see when we will square this and after squaring we will add it, what will be our result? You can see that rho square into cos square delta perpendicular plus sine square delta perpendicular, this will be equal to what? This will be alpha square minus beta square over alpha square plus beta square whole square plus 4 alpha square beta square over alpha square plus beta square whole square. So you can see the LCM will be alpha square plus beta square whole square, and this will be alpha square minus beta square whole square plus 4 alpha square beta square. And you can see this alpha square minus beta square whole square plus 4 alpha square beta square, this is simply alpha square plus beta square whole square and over alpha square plus beta square whole square, and this will be equal to 1. And so you can see this is also equal to 1. So we have get the result rho square equal to 1, and so it is found that rho is equal to 1. So the unknown constant which we have assumed here, this is simply equal to 1. Now you can find the value of this delta perpendicular by dividing this rho sine delta perpendicular by rho cos delta, and so we can find from here that and you can see this rho sine delta perpendicular over rho cos delta perpendicular. You can see what will be the value. This will be 2 alpha beta over alpha square plus beta square and over alpha square minus beta square over alpha square plus beta square. So this alpha square plus beta square will cancel out, and we can see this rho is also cancel out, and this is tan delta perpendicular, and this tan delta perpendicular, you can see this will be equal to 2 alpha beta over alpha square minus beta square. So this is the values of rho and tan delta perpendicular, and so the two unknown constants which we have assumed here is just found from this calculation. And let us say this is equation 4. Now we can find the value of the ratio of the amplitude of reflected wave and the incident wave in terms of these quantities. So you can see that E naught 1 prime over E naught 1 perpendicular. What will be this? You can see that this is alpha minus I beta over alpha plus I beta, and we have assumed that this is equal to e to the power minus I delta perpendicular, and from here we can easily found that what will be this delta perpendicular. Now you can see that tan delta, this tan delta, I am not writing delta plus, simply I am writing delta. We have seen that this tan delta is equal to 2 alpha beta over alpha square minus beta square. Now you can see this tan delta can be written as 2 over cot delta by 2 minus tan delta by 2. In fact, 2 over cot delta by 2 minus tan delta by 2, this has been written at the place of tan delta. You can verify it from the trigonometric formula. And so this can be written. And now this 2 alpha beta over alpha square minus beta square, this can be written as 2 by alpha by beta minus beta by alpha. You can check it. When you will take the LCM, you will get that this 2 alpha beta over alpha square minus beta square is equal to this one. So comparing the LHS and RHS term by term, you can see this cos delta by 2 will be equal to alpha by beta, and this tan delta by 2 will be equal to beta by alpha. So from here we can see that tan delta by 2, this is equal to beta by alpha. But here I have used the symbol delta perpendicular, so we can say that this tan delta perpendicular by 2, this equal to beta by alpha, and this is in fact equation number 5. So all the unknown quantities which I have assumed here have been calculated. Now we will consider the case number 2, which is when electric field is parallel to the plane of incidence. Actually, this delta perpendicular which we have calculated is the phase retardation, and similarly we will calculate the phase retardation experienced by after the reflection by the wave, considering the second case, that is when electric field is parallel to the plane of incidence. So now let us calculate the same quantity in this case. So case number 2 is when E is parallel to the plane of incidence. Plane of incidence. We have mentioned in the result B defined just now that in this case E naught 1 prime over E naught 1 parallel. This is equal to N2 by N1 cos theta I minus cos theta R over N2 by N1 cos theta I plus cos theta R. And if we take this N2 by N1 as a common factor, what will be our result? This is cos theta I minus N1 over N2 cos theta R, and over in denominator we again take N2 by N1 as a common factor. This will be cos theta I plus N1 over N2 cos theta R. So this will actually cancel out, and so what is our result? You can see that our result will be E naught 1 prime over E naught 1 parallel. This is equal to cos theta I minus N2 over N1 cos theta R over cos theta I plus N2 over N1 cos theta R. And we can write this expression as alpha minus I sorry, here there is N1 by N2, not N2 by N1. So you can see this is in fact N1 by N2. This is N1 and this is N2. And so I assume this cos theta I equal to alpha as I have assumed earlier, and N1 over N2 cos theta R is now written as I beta prime. And so this will be alpha minus I beta prime over alpha plus I beta prime. So here we have actually assumed that this alpha is equal to cos theta I, and we have assumed that this I beta prime is equal to N1 by N2 into cos theta R. We have assumed it. Now just like above, we can write that this E naught 1 prime over E naught 1 parallel. This is parallel, not perpendicular. Parallel. This is equal to, just I have written earlier, this can be written as this is e to the power minus I delta parallel. And as I have calculated just now, we can write that tan delta parallel by 2 is equal to beta prime by alpha, not alpha prime, but this will be simply alpha. And let us say this is equation number 6. So you can see we have actually calculated that the components of electric field vector parallel and perpendicular to the plane of incidence on reflection experience phase retardations, and these phase retardations are actually delta parallel and delta perpendicular, which we have mentioned here. But there is a phase retardation in the component of the parallel and perpendicular component of the wave, but there is no change in amplitude of these waves. It means the amplitudes of the waves remains unaltered or unchanged. So what we can see from here, let us mention it, that thus you can see the components of field vector E parallel and perpendicular to the plane of incidence. Plane of incidence on reflection. Experience phase retardation. Phase retardations delta parallel and delta perpendicular respectively. But there is no change in amplitude of these waves, but their amplitudes remain unchanged. Amplitudes of these waves do not change. So you can write that modulus of E naught 1 prime parallel E naught 1 prime parallel is equal to modulus of E naught 1 parallel, and similarly the mod of E naught 1 prime perpendicular is equal to mod of E naught 1 perpendicular. So you can see that each component for the each component of intensity, the electromagnetic wave which is totally reflected is equal to the intensity of the incident light. Since you know that intensity is proportional to a square of the amplitude, and since the amplitude of the reflected wave, which is in fact E naught 1 prime, and amplitude of the incident wave, which is E naught 1, since both are equal in both conditions, that is in parallel and perpendicular conditions, and so since the intensity is proportional to this amplitude and amplitude does not change, it means what? It means intensity will also not change. So you can see as intensity of the wave, intensity is proportional to modulus of amplitude square. So this implies that intensity of reflected wave is equal to intensity of incident wave. So if intensity of reflected wave is equal to intensity of incident wave, what does it mean? It means the total energy is reflected back, and this is the reason we call it total internal reflection. So this implies that the incident wave is totally reflected. So in this calculation we have seen that there is a phase retardation in the parallel and perpendicular component of the incident wave, but there is no change in intensity, that is the intensity of reflected wave and the incident wave is same. But now we can see that since there is a phase retardation in both the parallel and perpendicular component, so now we will calculate what is the relative phase difference between the parallel and perpendicular components of the reflected electromagnetic wave, and from that result we can discuss the state of polarization of the wave after reflection. So now our aim is to calculate the relative phase difference between the parallel and perpendicular components of the reflected electromagnetic wave. So now let us proceed to find this relative phase difference. Relative phase difference means what? It means the difference in the phase retardation of both. So now let us see the relative phase difference between the parallel and perpendicular components of the reflected wave. It is given as, if this relative phase difference between these two components is delta, then you can see this delta is simply delta parallel minus delta perpendicular. And from here you can see that this can be written as delta over 2 equal to delta parallel minus delta perpendicular over 2, which can be written as delta parallel over 2 minus delta perpendicular over 2. And so you can write this expression as tan delta over 2 equal to tan delta parallel by 2 minus delta perpendicular by 2. Now using the formula for tan A minus B, we can write this RHS as this is tan delta parallel by 2 minus tan delta perpendicular by 2 over 1 minus 1 1 not minus but plus 1 plus tan delta parallel by 2 into tan delta perpendicular by 2. Now you can see the above result, that this delta parallel by 2 is tan delta parallel by 2 is actually beta prime by alpha, and this tan delta perpendicular by 2 is beta by alpha. So you can write this as beta prime by alpha minus beta by alpha, and this is 1 plus beta prime by alpha into beta by alpha. And after simplification, taking the LCM, you can see this will be actually equal to what? This will be alpha into beta prime minus beta over alpha square plus beta prime into beta. Now we have assumed that what is the value of cos theta I and n2 over n1 cos theta r in terms of alpha and beta. So you have seen that alpha is equal to cos theta I, and this beta is equal to n2 over n1 cos theta r, and this beta prime is equal to n1 by n2 cos theta. Actually here the phase factor which is determined by iota I has been neglected, and the absolute value has been taken, and so beta is I beta. Instead of I beta and I beta prime, I have written only beta. So now you can see that this tan delta by 2 is equal to what? Let us substitute the value of alpha, beta and beta prime. You can see this will be cos theta I into n1 by n2 cos theta r minus n2 by n1 cos theta r, and over cos square theta I plus n1 by n2 cos theta r times n2 by n1 cos theta r. And let us simplify this RHS to some extent to get the desired result. You can see this is equal to cos theta I into n1 by n2 minus n2 by n1 into cos theta r. We have taken cos theta r as a common factor. and in denominator you can see this n1, n1, n2, n2 will cancel out, and so our result is cos square theta I plus cos square theta r. And you can see that this result can be written as cos theta I into n1 by n2 minus n2 by n1, and this cos theta, in fact during the discussion on total internal reflection we have found that this cos theta r is actually equal to n1 by n2 sin theta I whole square minus 1 square root. So this cos theta r can be written as n1 by n2 sin theta I square minus 1 and whole to the power half. And similarly in denominator you can write this is cos square theta I plus, instead of this cos square theta r, as I have written here, you can write this as n1 by n2 sin theta I whole square minus 1. In fact here we have used the result for cos theta r which we have obtained earlier in the lecture on total internal reflection. So now you can see what this result can be written. This is in fact equal to cos theta I, and now let us take this n2 over n1 as a common factor. When we will take n2 over n1 as a common factor, our result will be what? This will be n1 square by n2 square minus 1 and times n1 by n2 sin theta I whole square minus 1 to the power half, and over in denominator you can write the expression in this manner. This is n1 square by n2 square sin square theta I and minus 1 minus cos square theta I. You can write it. And now you can see this result can be written as cos theta I into n2 by n1 into n1 square by n2 square minus 1 into n1 by n2 sin theta I whole square minus 1 to the power half and divided by. Now you can see this 1 minus cos theta cos square theta I is sin square theta I, and so if we will take this sin square theta I as a common factor, our result will be n1 square by n2 square minus 1 into sin square theta I. And now you can see this factor n1 square by n2 square minus 1 will cancel out, and so finally you can see that what will be this result. this result will be actually equal to what? Therefore, you can see that this tan delta by 2 is equal to, here you can see that this n1 by n2 whole square, if it is taken as a common factor, so this result will be then what? This result will be actually in that condition, after taking it outside from the square root, it will be in fact n1 by n2, and that n1 by n2 will cancel with this n2 by n1. So finally we will get that this tan delta by 2 is equal to cos theta I into root over sine square theta I minus sine square theta I minus n2 by n1 whole square, n2 by n1 whole square, and over sine square theta I, sine square theta I. And so this will be this is our final result, and from this result you can now discuss the state of polarization of the reflected wave after the total internal reflection. You can see from this result that the value of this delta, which is phase difference between the parallel and perpendicular components, and you can see this phase difference depends on the angle of incidence theta I, but this theta I for total internal reflection is greater than critical angle, and so the plane polarized radiation after reflection becomes elliptically polarized, and the desired phase difference delta can be introduced between the two components of reflected light by the proper choice of this angle theta I. Since you know that the amplitude of the two components are different, so it is said that the reflected light is in fact plane polarized, is actually elliptically polarized, because if the amplitude will be same, then the light will be circularly polarized, but since the amplitudes are different, so in general it is elliptically polarized. Therefore, any desired type of elliptically polarized radiation can be produced by the method of total internal reflection. So you can see it from here that the reflected radiation is of course elliptically polarized in general, because the parallel component E parallel and E perpendicular are of unequal magnitude. So we say that the reflected light is in general elliptically polarized. So our conclusion is that delta, which is phase difference between these two parallel and perpendicular components, depends on theta I, and this implies for different theta I, but remember this theta I must be greater or equal to theta C. We can introduce different phase difference delta between the components E parallel and E perpendicular. And again we know that E parallel amplitude of the parallel again the amplitudes of E parallel and E perpendicular are different. Phase difference can be introduced, desired phase difference can be introduced taking the suitable value of theta I, but there is only one restriction, that this theta I should be greater or equal to critical angle. And at the same time, we found that the amplitudes of these two parallel and perpendicular components are different. So it is obvious that the reflected wave is in fact elliptically polarized in different state of polarization. So this implies the reflected wave is elliptically polarized. Elliptically polarized. So as I have told you earlier that after total internal reflection, we get the elliptically polarized electromagnetic wave. In fact, the incident wave is plane polarized, but the reflected wave is elliptically polarized. And the state of polarization, that is the phase difference between the two components of which superposition is elliptically polarized wave, can be changed in accordance with our design by changing the angle of incidence, but taking this restriction that this angle of incidence should be always greater or equal to theta c, because you know total internal reflection will take place only when the condition theta I greater or equal to theta c holds. So this is all about the state of polarization after the total internal reflection. The conclusion is that the incident wave is plane polarized, but the totally reflected wave is elliptically polarized.